So you do file and then what? Okay, so file, so the flag file, and then space for the name of the file, assuming the name of the pen and map file are the same, right? They're the same thing. And what if they weren't the same? What would you use? Pen and map, right? So if they're the same, you can use the file flag. If they're not the same, or it's, like I said, sometimes it can be a little glitchy, you can use the pen and map flags. So all you'd have to add here is the cluster and the genome one to run this analysis. And if you do that, you should get a file, an output file that has headings that look like this, right? Now some of these headings should look familiar because the FID, the ID, is something we've talked about earlier, right? Family ID 1, so it's the family ID of IID1, that individual. And the FID 2 is the family ID of individual 2 with IID being individual 2. Right? Now there's some other information in here, right? Some of which you can trust Planck, some of it not so much. And one of those, I believe the RT category gives you the quote unquote type of relationship. But I find more often than not that is incorrect. What you really want to look at is what column. For those who did this last week, what column do you really want to look at? The pi hat. Yes, pi hat, right? The pi hat gives you the relationship coefficient between the individuals. So if I were to ask you, how many individuals show parent-offspring style relationships with individual 64, how many already know that answer? Looks like some, not so much. All right, so what I want you to do, we'll give you about, we'll say 10 minutes or so. I want you to, if you haven't already done it, I want you to run the command that you see here, the genome in the cluster, right? With the data file that you created last week, the pen and map, and generate the coefficient of relationship output file that you see the heading here for. And then we'll regroup and kind of and talk about what we see in there.
I'm so good.
Don't forget, if you get tripped up, you've got the 2 help pages, and you can also use ChatGPT and Google to help guide you as well.
I'm gonna write this.
I think nothing sad, but I sound like
And then we like, everybody's like, oh my god,
Yeah, better. No, it's perfect.
that's so good.
What is the expected? I put it 0 to 1. The negative value is just called the average. Negative integrating? Or use 0.0. So the right scope is the more familiar one. And we actually, this is happening.
I'm so glad this happened because I have no idea what's going on last week. And now I know exactly what we were doing last week. Literally, like I was like losing my mind when he was talking. I was like, we're in week 6. I was looking at week 6 last night.
Even with genomic data, I don't always
Because I got confused as to whatever fucking flag is that I started doing. That's not a week 6 slide. Okay. You are less paid. Yeah, you can say towards the end, I just have a screenshot of it. I'll fix that up. Are you getting yes, that is correct. It is written down below. That's okay. That's literally me. I just feel like take part in the process. I got zeros. That's not Wait, let's put spaces on both sides. Hold on, I put both spaces. I got it from last week. It's
Every time he walks back,
Remember, you got two columns. So, is there a marker over here? No, there's not. We got so this applies to both of you guys who run at the same stage. Remember, you've got ID1. ID1 would be 1, 2, 3, 4, right? Compared to 2, 3, 4, 5, etc., right? Because eventually you're going to get 2 here. It's already compared to 1, so you're going to get 1 here. And 3, right? So you're going to get both sides. So you got to figure out how to grab both. There is one easy way to do it. Where you can literally just like filter one side and see how many of them are. What you want is like, there's 20 of these, and then filter the other side, and then draw on the other side. Or bioinformatics right now, I'll show you.
Yeah, that makes way more sense. I want to delete it.
You know how there's scary code and then
No, I want the scary part there too.
That's my background as well. That was using I used to teach at so I used to teach university. So I'm
Why am I like, I don't want to be like it is good.
All right, so we'll go through this. How many of you, just a little tip for those of you who are opening things in Excel, if you guys all take a second and take the file and open the file in Excel on your computer for me. I'll show you the little neat trick that some people, I think a few of you don't know you can do. So if you open the file, the output file, if you open it in Excel, and then you highlight the first column, so column A, right? That should highlight all the information in Excel. Right? Once you've highlighted column A, if you go to the Data tab in Excel, there should be an option to the middle, a little off to the middle to the right of the screen that says Text to Columns. If you click on that Text to Columns and go with a delimited option and pick the space option once you click next on that one, and then finish, it will put it in nice pretty columns for you. You can do that with any text file that you want. Right, so I'll say that again. If you open the output file in Excel, and then you highlight column A, because all the data is in column A, right? And then go to the Data tab, click on Text to Columns on the top right part of the ribbon, and then use the the limited option. There's a little tick, like circle, hit the limited, then click next, then check the space option, and then click finish. It will put the output in a nice little column for you. Okay. So, how many individuals show parent-offspring style relationships? How many have a number for me? Nobody? Very quiet now? Yes. Not 33. It's not high enough. Okay. Remember, you're looking for parents-offspring style relationships with individuals 64. So what number are you looking for? Behind me? I saw a hand go up. Behind me? What number are you looking for? Relationships that are what? 0.5, right? Or above, technically. Right? So 0.5, and remember, there are potentially the individual you're interested in, individual 64. It could be in column 2, IID 1, or it could also be in column 4, IID 2. You can manually do this by looking at it. I know lots of you are trying it away, but you can also run a pipeline to give you the same answer. So what if you run this pipeline that you should see on the screens now against your output file? What does it give you? 47. Yes, 47. Now, I will tell you, sometimes things work, and I don't know why. I don't know why that you need 2 full stops between the 1 and 64. It just works better that way. Yeah. It didn't work as well with 1.
Well, you know, it was
So hopefully you can successfully run this, and it will give you what is in that file. So what is this pipeline actually doing? Anybody? What's this pipeline doing? Right? Yeah, so it's basically grabbing all relationships. It's printing out the file, but it's not printing it. It's piping it into the GRET, which is grabbing all individuals between all comparisons between 1 and 64, and then it's grabbing those that are 0.5, and then printing that number of lines to the actual screen. So don't forget, the activity stuff's not recorded, so if you want to practice this script later on, make sure you write it down. I just added it this morning, it's not on the slides. So you should get 47. There are 47 individuals that have a parent-offspring style relationship with individuals 64.
Yeah, okay, whatever. That's awesome.
Oh, like it's not.
We get it working? We get number 47? 47, we get it working? Don't cut and paste it, make sure you type it all the way out. You might want to avoid the spaces between the heights, see if it'll work differently with that. Sorry? Before and after, yeah. See what happens. Sometimes I type quickly and there might be just random typo in there. So 0, so if you look at the file, is what's in the, what you think is in the file actually in the file? So then I would say, then try to step through the pipe and just say, okay, if I cat the file. Okay. That's the part that's the big issue. Like I said, it may work. It would work better for me if I had 2 full stops in there, but maybe if I had 1, it works. It would work better, yeah. Because it was being weird when I had it. So 0, yeah. Not the end of the world. Yeah, it's that F1 to an F64. I should have tested the script, sorry. Yeah, so basically it's looking for any relationship between 64 and anything else. So, there's multiple ways to do it. That's less concerning about than actually understanding what relationship you're looking for. Okay, so hopefully everybody has at least gotten the file. There are multiple ways to figure out the number of relationships that you found. You should find 47. We'll leave that for now. We'll get into what we're going to be doing today. Because we do have, because what we do today can take a little bit longer to actually get to run. So I'll get you guys to kind of like settle back down so you're listening, because you're going to need to understand this stuff before we actually do the activities. So last week we discussed the diversity and relationship in the broad sense. And this week what we're going to do is drill down further, and you will learn about runs of homozygosity analyses. So when populations are forced into decline, strong filtering of the available chromosomes in the population can occur. And the effect of strong filtering is that it reduces the effective population size. Right? Now, effective population size is the size of an idealized population that would experience the same rate of genetic drift or increase in inbreeding as the real population. Now, small effective population sizes, particularly where the numbers of males and females breeding are very imbalanced, can lead to increased genetic drift, which is of course the loss of genetic variation by chance, and it can also lead to increased inbreeding, which is an increase in homozygosity in individual genomes. Now, another force that can reduce genetic variation in specific local genomic regions is selection. Now, many domestic species populations have been subjected to selection by humans, usually for higher production capacity or higher product quality. Most of this selection has happened by humans choosing to breed from individuals with superior performance, but they didn't exactly know how the genes were being selected, and they didn't know what genes were being selected. So however, since geneticists can use the characteristics of genomic variation in a population to show which parts have been strongly selected by humans, genomics opens a whole new world. Now, one approach often applied is what is known as a run of homozygosity analysis. Now, runs of homozygosity analysis in each individual detects inbreeding when pedigrees are unavailable or don't exist. And the sizes of runs of homozygosity segments can describe the general distance to the last common ancestor. And runs of homozygosity analysis looks for overlapping runs of homozygosity within individuals in a population to detect selective sweeps. And sweeps can be the result of natural selection or artificial selection. So artificial selection being basically human intervention. And averages across the population can detail population levels of inbreeding. So what are runs of homozygosity? Well, individual genomes are typically comprised of homozygous and heterozygous segments. And as you see here, in the light blue are homozygous and the dark blue are heterozygous. And the size of a runs of homozygosity segments are determined by the population linkage disequilibrium. Runs of homozygosity segments are typically shorter for unrelated animals and longer for animals with more recent common ancestors. And runs of homozygosity segments are typically shorter in outbred populations and longer in inbred populations. So for a closed population, which many animal breeds are, you're almost certainly going to see some short runs of homozygosity because they have a common ancestor pool. Racehorses, thoroughbreds are a prime example of this. Right? They're always going to show some level of relationship because they started from 3 stallions. And so no matter how far back you look, they're going to have small fragments of that, regardless of the horse and the breed. Now, there are 2 types of runs of homozygosity. One that refers to the individual, and one that refers to the collective runs of homozygosity in the population. If you were to overlap the information seen in the previous chart, right, so the graph that was there before, across multiple individuals, it is possible that you would see, or it is possible to see if any regions are highly homozygous for the same region or haplotype for the population. So if you look at this figure, what must be happening in this region to make it so uniform in the global population? So you see on the left is just the amount of homozygosity, right? So you see there's a region there highlighted. What must be happening to cause this to be so uniform in the global population of this breed? Yes? Yep, here from both, yep, you're both correct, yep. Strong phenotypic selection, right? So something that they desire, that humans desire, it says I think a dog breed, right? I believe Doberman, based on the photo there, I probably put it in there for a reason. All right? So, could be genes under selection. What else could it be? There's going to be a phenotype, right? What else? Don't think positive, favorable stuff. Think unfavorable things now. Well, it could be inbreeding, but it could be something where the breed has a natural, there's a biological advantage, right? So it could be an important area associated with risk of a certain genetic defect or disease. So it's almost fixed in the population because it's resistant to a certain disorder or disease. And that's, of course, very useful in terms of breeding and all that. So you see a much higher level in the population. All right? There are 7 such, quote-unquote, swept regions in Doberman. So this is Doberman, right? Should people push for more diversity in this region? Diversity is always great, right? Or what did we say last week?
Diversity is not always great.
Not always great. Why?
Well, I'm not sure but like with dogs, if they're selectively bred, like for instance, boxers, you get like an MDR1 gene, you get brachycephalics where you're ingraining bad traits and reducing their fitness.
Okay, so this could be something that's associated with a health trait, right? That's a favorable health trait. Why would you want to introduce something that may risk the health of the animal, right? So it could be a disease resistance gene, things like that. So just because there's not a lot of diversity in this region of the genome doesn't mean that we should introduce more diversity into that part of the genome. So back to our friend Plink, all right? So there are multiple options for executing a runs of homozygosity analysis. However, since you guys have already been using Plink, we're going to use Plink to run the homozygosity analysis as well. There are a variety of softwares can do it. Most of them take the same behind-the-scenes approach. Plink, as I mentioned before, is widely used in a lot of the domestic species, especially cats, dogs, some of the companion animals. So before you attempt to do a runs of homozygosity analysis, there's a couple things we need to touch on first in regards to how these analyses actually work in Plink. So, runs of homozygosity is essentially done by in a stepwise fashion. So the defined window stepwise scans an individual's genome and scores for each SNP the proportion it appears in a homozygous window. Right? So here you see an introduction to the concept of how the scanning window works. In this picture, homozygous SNPs are blue and heterozygous SNPs are in gray for a single individual. So we're looking at a single individual here. While we have a frame that includes 5 SNPs, the box that you see there, the data presented beneath the figure are relevant to each individual SNP. The first scanning frame here includes 5 SNPs, all of which are blue, therefore they are all homozygous. And the numbers underneath count the number of times a marker is in the frame. That's the first one, so times in the frame. The next one, the number of times every marker in the frame is homozygous. And the final number, the proportion of times the window frame is homozygous. Right? So those are what those 3 numbers, the ones mean at the bottom. So if we follow this pattern until the 6th SNP, right? So 2, 2, and 2 again. How many times in the frame? It's been in 2 frames. Right? Times in a homozygous window. Both times it was in a homozygous window, so it gets a 2. And then the proportion of times the window is homozygous, 1. Right? This is 1, entitled like 1 out of 1, or 2 out of 2, right? So if we keep following this until the 6th frame, the 6th SNP, window size is still 5. Really no difference between SNP 5 and SNP 6, right? Yet. However, things start to change as soon as we start including SNP 11, right? If we're looking at individual, like SNP 7, how many times has it been in a frame, right? It's been in 5, it can be in 5 is the most it can be because our window frames are 5. How many times has it been in a homozygous window? Well, the first 4 times, first 4 frames it was in, they were homozygous. But now we've input a heterozygous SNP in there, so it's only been 4 times in a homozygous window. And that results in a proportion of what? 0.8. And if we play this out, you can see it changes again when we get to the one that has 2 heterozygous SNPs in there. And this is what a runs of homozygosity analysis does. Any questions about that? For those who want to hear it a second time, this is all being recorded, so don't worry about that if you didn't get it on the notes, it is recorded. So, what's interesting here is there are certain thresholds that are set when it comes to runs of homozygosity analyses. So if we were to allow 1 heterozygote in our runs of homozygosity, then the ROH here would include SNPs 1 through 8, right? Because they would only have had 1 heterozygous SNP. If we do not allow any heterozygotes, then the ROH, so the run of homozygosity, because they're going to be in sections, right? So how long is our run of homozygosity? Well, it would be 1 through 8, it'd be 8 long if we allowed 1 heterozygous SNP. But if we said no heterozygous SNPs are allowed, it would be 6. Why might we allow a heterozygous SNP? Like it's a run of homozygosity, so why in the world would we allow a heterozygous SNP to be in there? Any ideas? Yes. We're not concerned necessarily about the inheritance right now. We're just concerned, is it homozygous, is it heterozygous, right? So it's not because of a random mutation, because we still want to know that it's not now, it's no longer homozygous. So why might we count it as homozygous even though it isn't? It could be a misread, right? It could just be a genotyping error, right? We're only looking at a few here, but we said the arrays can have as many, they have hundreds of thousands of markers on them. And by chance, there could just be a mistake. Okay? You also might see a similar threshold for missing, right? You could have one that's missing. Do you count it as homozygous if it's got a missing SNP, a no call? Well, it could be homozygous, but it may not be. So remember last week we were looking at, okay, with a margin of error, it would be one answer, with no margin of error it would be another, right? So it's the same thing with Runzo homozygosity when you're setting your thresholds. You may want to include a heterozygous option of 1, just to account for potential genotyping errors. So how do we do this in the analysis? So you have to set parameters. So Runzo homozygosity analyses are a little more advanced than what you were doing before, where it was just 1 or 2 commands. There's quite a few more commands and parameters that must be set in order to run these analyses. And here you see them, right? So far, you can see, oh, what's happening here? My computer's being... Sorry guys. Sorry, my computer's having a little bit of a panic attack. It doesn't want to show the figure anymore, but hopefully it'll pop back up. So we said that most defaults, I think I mentioned before, most defaults on programs are going to be human. What if you're not working with a human? What if you're using this for dogs, cats, pigs, horses, cows, plants, right? You may have to adjust the number of chromosomes. So when it comes to chromosomes, N is going to be the highest autosomal chromosome number for the species you are choosing. Right? So in humans it'll be 22, in other species it will vary, right? And there are 2 methods for telling the program what species you're working with. You can use the chromosome set number, you can set the number of chromosomes, or you can cleverly find the shortcut that Planck allows, where you can specify directly the species that you are working with. And when you do that, it automatically knows how many chromosomes there are, and you no longer have to tell it how many chromosomes. Oh, there it goes, back up. So we also have the window parameters, right? So the homozygous window SNP, you see it in the top left there. That's to change the definition of the window select frame for scanning the window. So how many SNPs per frame or window? That's what that's affecting. You also have other parameters that need to be set. So the final Runzo homozygosity analysis. So there's the sliding window size that you're setting, but you're also setting the parameters on, okay, in order for it to be considered a run of homozygosity, what criteria must it meet? Right. And these are the homozygous SNP, homozygous kilobases, density, and gap. And these are going to be constraints. So if you look at the SNP KB one, the homozygous SNP, homozygous KB, this determines how many SNPs must be included or the range they must cover to be considered a run of homozygosity segment. So is it really a run of homozygosity if there's only 2 SNPs next to each other that are homozygous? Or do you need 100 SNPs next to each other? Or 10 or 5, right? Parameters are up to whoever's running the analysis. The density is the minimum density it covers. So 1 SNP per 50 kb, so how close do they have to be together? And the gap also influences that. So the gap is going to be the maximum interval between 2 markers. So think about this in a practical sense. If 2 SNPs are too far apart, should that segment be considered homozygous? Should that segment be considered homozygous if they're too far apart? What might be an example of this? Well, maybe you're going down the chromosome and you have a few homozygous SNPs, and then you hit the centromere, and then you don't actually have anything homozygous until you get to the other side of the centromere. Right? Do you really want to consider that one homozygous SNP, or should you break it up and say, like, okay, this is a smaller homozygous run, and on the other side of the centromere is another run of homozygosity. They're just 2 separate runs of homozygosity, not one continuous massive run of homozygosity. Right? So they do need to be within a certain region on the chromosome. And of course we talked about the error rate, so the homozygous window missing, and the homozygous window het. So how many heterozygous are you gonna allow in there to be considered homozygous, and how many missing are you gonna allow? Right? And all of these information is also on the help pages in great detail for those who wanna learn a little bit more about the behind the scenes of what's going on with these runs of homozygosity. Now, there is some insight that can be provided when it comes to what the thresholds for these should be. So, you can determine basic levels of LD in the species you are working with. And this will help, you can also determine what the error rate of the array you're looking at, you're using is, and these can help you determine what these thresholds will be. So how do you choose the parameters? Well, SNP density tells us an appropriate window size in KB and SNP number per window, and the expected gap between markers. You could configure, or you can actually figure out LD from the data itself. If you have array data, you can estimate LD from that array data. You also have marker accuracy, which informs the acceptable heterozygosity rate per window. So if you have a marker accuracy of around 98%, so if your array has a 98% accuracy, then that means what, 1 het per 50 SNPs would be incorrectly called. So if your window size is 50, or your run heterozygosity size is 50, you may want to include at least 1 heterozygosity call in there to account for that. You also have the genotyping rate, right? So, which informs the allowable missing rate. Now, typical call rate is around 98%, so 1 missing per 50 SNPs sounds about right? And this adjusts for the accuracy of the array as well. Now, factors may change based on how the samples were derived, if it's low-quality DNA versus high-quality DNA, and also if you're combining multiple arrays, so old arrays with new arrays, you might see an increase or decrease in the density of markers on the arrays, so you may have to adjust your thresholds accordingly. So let's look at an example of how to choose parameters. So LD in the dog extends about 500 kb between 2 markers. So the genome for the dog, as you see here, is 2.5 gigabases. That's 2.5 times 10 to the 9th. The canine array contains 220,000 markers. And within breed LD is 500 kb, so with around 50 markers per LD segment of 500 kb. All right? So 50 markers per LD segment. And the array genotyping accuracy is 98%, and the genotyping success rate is 98% as well. So how would you factor this into your run-out homozygosity analysis? Well, like this. Okay, the homozygous SNP is going to be 50. Okay. The window het size is going to be 1, and the homozygous window missing is going to be 1 as well, okay, based on the information available here. So parameters from window size are set from your pre-existing knowledge of the genome characteristics, including the size and expected LD, right? And hopefully you've seen how to calculate these in previous units of study. And the parameters for heterozygosity and missingness are dependent on the array performance characteristics. So some of the parameters are set based on what you know about the genome of that species, and the other are based on what you know about the parameters for that array. And the array parameters are pretty widely available if you're using them pretty regularly for a certain species. Usually the array platforms can tell you what they are as well. So ultimately, runs of homozygosity analyses are used to understand selective sweep in populations, as there are multiple situations where it might be of interest to know more about genetic fixation in a population. Now, genetic fixation is truly a lack of diversity, right? Because something is fixed. So this means that in regions of the chromosomes that are affected, pure breeding, I put that in quotes, populations are pure breeding populations of individuals will always be homozygous for the same gene variants through the region because they are fixed in that region. If these regions are extensive, then during recombination, like genetic material, will be exchanged with like, further reducing genetic variation, right? If something is fixed in the population, that means there is no variation. So barring a spontaneous mutation, you're not gonna see any change whatsoever. Now, if the fixed chromosome region is completely healthy, then this may be of no consequence, right? Okay, it's fixed, the population is very healthy. But if it is a disadvantageous allele that is present in that region, then a pure breeding population may be left with no means of avoiding outcomes associated with disadvantageous alleles, right? Now, those alleles may start off as advantageous, and you might see an environmental effect come in that makes them disadvantageous. What could be an example of that? What might be an advantageous trait at one point, and then something in the environment changes, and now that allele that codes that is now totally not to the advantage of the animal? I see a hand up over there, yep. Exactly, I was thinking the same thing, right? So the classic example is with moths, right? If you have a moth that's white because there's snow everywhere, that's an advantageous mutation, right? You guys saw white marking gene earlier this year, right? Was it MITF, right? MITF, right? Associated with white spotting, right? So there was an advantageous phenotype associated with that marker. But if all of a sudden climate changes, now there's no snow there, it's just rain, everything's brown, and this white moth, because you have this mutation, if there's no variation in that species, they're all at a major disadvantage, although it may have been an advantage prior to that, right? So it can change. So that brings us to start of today's activities. So if you haven't already, go ahead and slide your virtual machines back up, because I'm sure they've all turned off. But still listen, because there's a little bit of stuff that you can do while they're turning back on. So the NCBI genome database is the best source for information about the characteristics of a genome. You guys have used it a few times already. And it is a helpful place to begin for many species. So it gives you a bit of information about the species. Now, always use information from a complete genome or a quote-unquote full draft genome, since these are expected to cover more than 95% of the true genome sequence. Okay? So you always want to use a complete genome. Now, if you recall from week 1 that we were able to use the genome database, so genome in brackets, right, from the ncbi.gov to search for the status of a reference genome for a species of our choice. So go ahead to that website, NCBI, the genome browser, and select genome from the pull-down menu labeled all databases. We have the browsers open. All right, so once you've selected genome from the pull-down menu labeled all databases, I have a question for you. What is the current predicted genome size for koalas?
NCBI, not PubMed. And then where it says nucleotide, you'll click all databases, you'll change that to genome.
And if you think you found that already, I will add the second question. What is the current predicted genome size for an apple?
No, it's all right. I see how it is. It's fine. Oh my God, I'm very sorry to hear that. Self-agent or I swam in that. This is literally my voice. Literally my voice. No, I did that. Like, it's really covered. This hair's really,
Yeah. Yeah, so I'll get back. There's usually multiple genomes they get like reevaluated and everything like that. So you just pick the one with the check mark because it's the genome that's.
You know, it sounds so like you don't have to talk about it.
Okay, what is the current predicted genome size for koalas? Nobody knows current genome size for koalas? Yeah, 3.2. How many got 3.2 gig, right? 3.2, yeah? And where did you find that information at? Under reference gene, right? So if you click on the reference one, there's other insight. It gives you at the bottom, tells you the statistics of the genome, right? So it's not something you have to calculate or determine. It will give it to you, right? And now, from NCBI, what is the predicted genome size for apples? What? 650. How many got 650 megabytes? How many got something different?
Did you get something different?
You have the same as the caller, you're looking at someone who's looking at the wrong spot. So you can have a look, see? So how many got 650? How many got something different? Stupid Apple genomes. So I have a note in my notes saying 650 is what it was the year before last. And then last year they updated it to 703 megabases. So there must be a new genome out. And I have not updated my notes. So if it's got the green tick, that's going to be the current reference one that's like the frequent. 650, yeah. So that means they must have put okay, yeah, so Eloise is saying they must have put out a new genome, reference genome for apples. And Eloise is telling me it's telomere to telomere. So the genome varies in size. I was just telling Mitch. So if a new genome comes out as a reference, you might see that it gets a little bit bigger or a little bit smaller based on the new reference. So it sounds like the new one's 650, which is good. If you found the koala one, it's fine. So all seems good. So that brings us to the next thing. Collecting information about LD. Remember I said genome size and all that, publicly available? You have to find that based on what you know about the genome. Same thing with the information about LD. Publications are great because they allow you to immediately look up the expected population LD decay. However, the predictions will only be a rough guide for the population you have at hand. You can also calculate the LD range from the data that you have. Now, LD decay is the process by which the correlation between genetic variants weakens with increasing distance due to recombination. Hopefully you guys are all very familiar with that concept from previous genomics units. It's a fundamental concept for the understanding of genetic structure, mapping traits, and interpreting genomic data. So LD always important. What is the expected LD of decay for apples? And I will tell you now that it can be found in this paper, which I believe is on the Canvas page for this week.
Sorry guys.
Make sure you're jotting down these numbers too. You're going to need them for the activity that's coming. In my notes.
Yay! I love it when we get the same energy. That's what I'm doing. I feel some blood in
I've been willing to colour the actual just like colour all the things.
You go to that.
Colour all the things blue, all the easier time. Colour all the things does he see nodes on the web?
Not necessarily. Just keep it.
Are there no glasses for it?
Yeah. We do nothing with sickness clothes. I was wearing them like if I didn't have to walk in the rain, I would.
Okay, has everybody found it? It's in the paper, you just gotta read it. Right, what did we find? What is the expected LD decay for apples? Yes? No. I'm just kidding.